right, thanks very much. Honored to be able to come and present some of the successes and the challenges and lessons learned that we've had in the steelmaking coal mining industry. Also like to introduce Kareem Balkan is here with us today as well. She's the Director of Occupational Health and Hygiene for Teck Resources, as well as Chris Rogers, who's the Senior Data Scientist that has been instrumental in some of the findings and the work that I'll be sharing and presenting with you here today. Quick overview, we'll just touch on Teck Resources and Teck Coal, what we do. Also, we're going to go over at a real high level of what the steelmaking coal mining process looks like, what some of our operations do, and we'll also touch on what our key exposure agents are as well, and what we focus our efforts on. Then we're going to touch on real-time personal best monitoring and the methods we've developed around that. We'll touch on engineering control, specifically looking at cab ventilation. And then share some preliminary findings that we have from our real-time area dust monitoring for in-pit environments. So really excited to share those as well. All right, so let's talk a little bit about Teck. So Teck has been around for about 100 years in Canada. Certainly a large organization. We have 11 operations in total across North and South America. Looking at our copper operations, they span from North America here in BC. Actually, Highland Valley Copper is one of them, right outside the Kamloops area. And then in South America, we have a few, especially with one that's under development and soon to open very soon. Our zinc operations, we have a mine up in Alaska, and then we have our smelter, which is located in Trail as well. And then there are steelmaking coal operations, which is going to be the focus of what we're talking about here today. And I'll give a little bit more detail on that. But from here on, we're looking at steelmaking coal. So that's to have a little icebreaker here. We got a first poll question and want to gauge what's the knowledge of the group here. So what do you think steelmaking coal is used for? Two options to choose here. Is it used to, oh, am I meant to
You're okay.
minimize that or?
Nope,
we're okay?
just.
Oh, it's on there. Okay, good stuff. Okay, so steelmaking coal used to be burned to generate heat to make power, which is then electrically heating up furnaces to make steel? Or is steelmaking coal actually a key ingredient that reacts with iron ore to produce steel? What do you think? I'm just looking at Colleen here for guidance on when to check in.
Those are your
Okay.
results.
Okay, so online the poll thinks 71% it's used to react with iron ore as a reducing agent as part of the steelmaking process. What are the thoughts in the room here? Who votes for A? Who's getting influenced by B or knows B? All right, good stuff. That's exactly it. Okay. On this one? Yeah, okay, good stuff. Okay, so yeah, B is the answer. Correct. Okay. Let's go back. Can I get rid of the menu along the top there?
Yep.
Yeah? Okay. Thanks. I'll let you do that. So yeah, steelmaking coal is fundamentally different from thermal coal. Right? It's this key ingredient that we need to make steel. Right? And what is that steel used for? Well, we got to obviously use it for our infrastructure, bridges, etc. So what this shows is some of the examples of how many kilograms of steelmaking coal it takes to make the steel to make these things in life that are essential for how we live. And then, of course, as we talk about our infrastructure to produce electricity for, going electric, how much steelmaking coal it takes to make a wind turbine. How about your car, right? 600 kilograms for the average car. So when you think about an electric car, there's a lot of steelmaking coal that went into making that, as well as our rapid transit as well, too. So it's one of these key ingredients that we need. No, that's all good. Yeah. Thank you, though. All right. So just talking specifically about Teck Coal and our operations. We are located in the southeastern part of BC, which is the Kootenays. It's a beautiful spot in the Rocky Mountains. I've got some pictures here to show soon what kind of environment it is. Pretty large mines. We got about 5,000 people working there as like full-time employees, right? And this isn't just like mining operations. This is also in our business unit operations. And that's also our supporting operations, such as our mine effluent water treatment facilities as well, too. I'll just give an example of our location where we are. Fernie is kind of like a closest thing to a resort town. Think about like Whistler or Banff. Fernie's got world-class skiing and all the other fun stuff like that that goes along with it. And this is all part of one valley here. So you can see some of our mines are located close to the communities of Sparwood and Elkford, where a good proportion of our workforce lives in this area. I live in Elkford, right? Nice and close. My commute is very easy. One thing I want to touch on too is our contractor workforce. And this is typical in the mining industry, is that you bring in a lot of contractors, especially around shutdowns and other specialized operations. So kind of the stat is on that is that we have about up to 10,000 contractors that support our operations, and it kind of pulses up and down depending on what the process operations shutdown, mill shutdowns, et cetera are. Right, our team. I recognize maybe at the back it's a little tough to see this, but I want to touch on our team who supports these operations and is advancing occupational health and hygiene. So at our corporate level, we have a Chief Medical Officer, Dr. Joshua Tepper, with dotted line responsibility to our lead occupational health nurse, who also has an occupational health coordinator working with her as well too, specifically focused on that. Corinne Balkin, as we mentioned here, she is our Director of Occupational Health and Hygiene, and with dotted line responsibility to me. Corinne sets our strategy and where we're going. And what we've achieved has been much in part to what Corinne has established in her years of being with Teck Resources since 2015. 2015, 2014? 2015, absolutely. So myself as the lead at this point here, sharing kind of what our team structure is, having 2 direct reporting occupational hygienists, supporting our business unit and our water treatment facilities. And then each of our operations has an occupational hygienist as well. And as you can see that they have teams that they work with, often this team size represents the size of the operation as well, how many people are there. So we have occupational health and hygiene coordinators, and we also have co-op positions as well too. So, and then we have also got our technology and innovation team who helps supports some of the technology we're applying to advance health and hygiene. So that's Chris Rogers, for instance, being the senior data scientist there, as well as our deployment specialist product owners. Sorry, I do have a cough, getting over COVID from a couple weeks ago, so I will cough at times. And one thing I want to highlight too is we have quite a few alumni, right? And that's denoted with the UBC symbol there. So Nicole Boder is with our technology and innovation team. So we have a hygienist embedded in there, which is super awesome. And we've got Erin Birch as the hygienist at Green Hills. Angeline Forbes-Salmon, she just graduated last year. She's the occupational health and hygiene coordinator at Elkview. Terrific opportunity to transition into these roles through a coordinator position. And of course, Corinne and myself and Chris as well. So just want to highlight, we've got a lot of career opportunities with Teck Resources. And this is just Teck Coal, right? There's the Smelter Trail, there's Highland Valley Copper, there's other operations. So just want to highlight that, and then also the co-op opportunities. We're looking for 4 co-ops for this summer, right? Same as Trail, and Highland Valley Copper is interested as well too. So really want to encourage you to apply for those. And Corinne and I will be hanging out afterwards here. We're more than happy to talk about career opportunities and co-op opportunities. So please take that advantage. We're here in person because we want to engage. All right, and just, of course, I got to give a little plug on the co-ops here, and just shared some of the highlights. So at the end of every co-op term, the students give a presentation back to our Occupational Health and Hygiene Committee, which I just shown the team there. And they also do this for their senior leadership at their site. So just a few examples of, like the activities that happen. We value work-life balance, right? So you get out there and enjoy the outdoors. That's a big thing there. But also a lot of learnings and professional development that you can achieve during those times there. And you come and join a community of practice. We have monthly meetings, quarterly meetings, etc. We've always got each other in a team at the end of the line, right? So it's great to join that kind of a team. So a lot of opportunity. All right, let's get on with the business here about mining. And let's talk about how we actually mine. And so essentially, when you look at a mountain in the Rockies, as the classic picture shows many layers. And for us, in our mountain ranges, what we have is this metallurgic coal that sandwich in almost like a layer cake. So our operations, and this could be at ridge lines, this can be down into pits as we work our way along. The whole point is to release that coal, and we do that with drilling and blasting. And then we go in, we remove what's called the waste rock, and then we go in, and this is a perfect example right here. That's a coal seam, where you have a shovel that's digging that out and put it into a haul truck. And the haul truck's taking that down to our processing operations. We're moving a lot of rock. Typically, we have about 10 parts of waste rock to 1 part of coal, right? So we got a lot of waste rock to move with our haul trucks, as well as what we call our ore body, the coal that goes to the processing. Our processing operations is essentially refinement of the coal, and through those processes, it gets put onto rail cars, and the rail cars come down to Vancouver to Neptune terminals or up to Prince Rupert, and it gets shipped out. And that's what we call seaborne coal. It's taken overseas and off to go make steel. So with all these operations that we have, there's a heck of a lot of maintenance required for it. So in our processing facilities, we have annual shutdowns, ongoing maintenance. Think about it, there's a lot of metal and a lot of welding going on, right? And then when we talk about our mining operations, across our 4 operations, we have well over 400 pieces of heavy equipment. And we're talking massive, massive pieces of heavy equipment. And you can look at the size of this one facility. The example at the bottom left here is Fording River. And this is how big all the maintenance is happening for that one site there. And just a little factoid for you, the reason it goes from being really small here to big is that on the right-hand side is what the shops were originally sized for back in the late 60s when this mine started operating. And over time, the equipment has gotten bigger. So that's why these buildings get much bigger at the end, is because we need that space. And you can see the picture on the right gives you an indication. That's a 400-ton haul truck, an ultra-cast haul truck, right? And we can fit many of them in there and have concurrent maintenance activities going on. So as a hygienist, you start thinking about, hey, what are the exposures that could be happening here? Now, I talked about our supporting operations, and that's what we see here at the bottom right in the pictures, our water treatment facility for mine effluent. We've invested billions of dollars in meeting our water quality goals. And we have these active water treatment facilities, which are significantly huge. I guess you probably can't see the detail in the room here, but for those online, and some really advanced processes for fixing selenium and nitrate and removing it from the water so that you got clean water going back into the creeks. All right, so based on what I just told you, let's do another poll. We'll do a quick check here. What do you think? Which agent is our highest risk based on the number of people exposed and the severity of outcome? So I gave you 4 options here: silica, coal dust, welding fume, or noise as a steel-making coal operation. All right, let's do a scan through the room here. Raise a hand for everybody. Who thinks silica is the #1 agent? Okay, got a bunch of hands. How about coal dust? Who thinks coal dust is the #1 agent? Okay. Welding fume? Noise? All right. All right. So the answer to this, and I'll just, we can see what the poll shows online here is 60%. And it was about similar in the room here for silica as well, too, as being the #1 agent. And the answer to that is silica. Silica is our key exposure agent. Why? Well, it's the number of people exposed and who would be at what we call a hazardous exposure level. And the thing is that the ACGIH exposure limit, 0.025 milligrams per meter cube, it's pretty low, right? You hit that threshold pretty quickly. Typically, people think coal dust is what it is. But the coal dust exposure limit is almost 30 times higher than silica, right? So it takes a lot more exposure for that. And remember I told you about that 10 parts of waste rock to 1 part coal, right? You're not finding significant coal exposures out in the pits because of that ratio. It's in your processing facilities where you find it, where you have that refined ore body, and that's where those more elevated exposures occur. So it's silica. The most number of people and the severity of the outcome from silica exposures, chronic repeated exposures. Now, of course, coal dust, absolutely. Welding fume, absolutely, and noise. And these are what our teams are focusing on with a risk-based approach. So we're focusing on getting control over these key agents. All right, and our vision. When focusing our efforts on these agents, our vision is low and moderate risk, similarly exposed groups. Right? And how we're achieving this is with engineering controls and using real-time technology to help direct us where best to apply our efforts. Okay, so on that vein, we'll head into looking at real-time personal monitoring and the methods that we've been working with to help us achieve this vision. Before we can really get into that though, we got to understand some of the limitations of personal real-time monitoring. And the International Council on Mining and Metals has a great paper out highlighting what some of these limitations are. Right? And so when we look at results, we need to keep these in mind. Right? There's no standardization of sensors. And so you got to be cautious when you're using different instruments. There's no standards on the use of the equipment or application of its data. Right? So you go get this instrument, but then you got to figure out what to do with what the output is. There's limited speciation of the air contaminants, very limited. Like it'll tell you what the estimate of the dust is in the air, but it's not telling you what type of dust it is. Okay, there is one new area monitor that does some silica element to it, but it also has some limitations and strengths. You got to calibrate as much as you can for that particle, so you get the most accurate reading based on the profile of the particle that you're measuring for. There's interferences from other particles in the air. Fog and humidity can all of a sudden make your sensors go crazy and look like it's really dusty when it really actually isn't dusty. You got to consider the size of the instrument. And again, pretty good nowadays for personal, you can wear them, right? But how about power requirements? Is it going to last through a 12-hour shift? And how about outdoor area monitoring? You're dealing with solar and batteries and that kind of stuff. They're key. Interpreting the data. Right? You get these massive data logs coming from them. And you got to be able to interpret that. It's not just one method. And then the labor and expertise to actually get meaningful findings from that data. Right? So it takes a lot to make that happen. So therefore, we dove into this and try to make utility of it. And before we go there, consider traditional monitoring. Right? Traditional monitoring, the value is you get a sample on somebody. And if you're confident that it's representative of their work and their work conditions, right? And often you're relying on field sheets or interviews with workers, that kind of stuff, and we send our sample off to the lab where we have a high degree of confidence in the results that we get back there, right? But you get one number back, and that's it. And as a hygienist, you're then left to interpret why did this happen, right? And you go into those field sheets, you're going to meet with somebody. It's a very qualitative approach at that point, right? So the beauty of real time is that you get this profile. You get a time series of what that exposure was throughout the shift. But it's what the sensor detected and estimated. It doesn't tell you why that happened, right? Or what were some of the contributing factors to it. So that's really the big lift there, and that's what we tried to get into and figured out a way that we can get meaningful data out of this. So I'd like you to focus on the image on the left. So we got an individual working on our pit. They're wearing a real-time personal monitor. And this is a clip of what the data looks like coming out of it. We have it at 1 minute averaging for intervals. Imagine 12-hour shift, you got 720 lines from this, right? And what you get is your average exposure for a 1 minute period, right? And a bunch of other variables, the flow rate and that kind of stuff. But the key one here is your mass concentration and the flow rate. So what we've done is deploy job shadowing in the field. Right? And then what this job shadowing does is we're able to task stamp every minute of these values of what that person was doing and where they were. And we standardize as much as we can what those terms are, so you got like a clean data set from it. And at that point, you can start to interpret the data, right? And you can start to aggregate it. And so what I'm sharing here is our formula that we have here. And what we've done is we've worked backwards. And we've taken this average mass concentration and dividing it by the flow. And what you get is the actual estimated weight of dust exposed for each minute. And what you can do at that point is add it all up per task. And you actually get an estimate of the overall weight of dust for the entire shift. And with that, with this formula at the bottom there, you're able to determine what percent of exposure was due to the task somebody was doing at that time. That's how we're starting to get to interpret this. And I'll give you an example. So this is a personal sample. I know you can't see it because of the menu, but it's a case and it's our power line crews. And what we're able to provide is a time series, right? Classic thing. We do have exposure limits as a reference point, but I do want to touch on this is that with real-time detection, you can like say, hey, where was it at? But you don't make definitive statements on exposures with real time, right? There is inherent error with the sensors as we talked about limitations. And this is actually the total respirable dust on the upper profile here. And what we do is we scale it down for silica, right? Because we have a very good idea of what the percent of silica is for our similar exposed groups based on traditional modeling. So they get a good idea of what that profile looked like, but really this is the key thing on a personal report, is in the top right-hand corner, is we're able to rank each of these tasks that the person was doing during their shift and which contributed the most of their exposure. Incredible learning for your workers and the workforce at this point, because they actually understand what happened and what contributed the most. And some of the best controls are the ones that come from the shop floor, from the field. I mean, that drives it. So huge learning with that. And then of course we do report back filter-based results that were sent back to the lab, right? And there we do make some definitive, determinations on were you, low exposure, moderate exposure, was there overexposure? Makes we have a high degree of confidence in that, especially with our lab sample. So that's how we're able to extract that meaningful data. That's a personal sample, right? And the key thing is that we don't make decisions on one sample, right? We want to get some more power out of this. So what we do is we can aggregate these results. And that's exactly what this example does, showing you once again for the power line crews, when we aggregate those task-based results together, right? And this is very powerful for when you're making decisions on where to focus your efforts for exposure controls. And what this shows here on the left is the exposure contribution by task group, right? So line work, and I know it's tough to see at the back, but 38% of the exposure for that seg, and this is across seasons, right? We randomize it as much as possible, is due to line work. And of course, hey, look at where they are. They're outside, right? Now, where do we deploy our controls there? That's a pretty challenging one. When somebody's up on a pole, it's probably gonna be respiratory protection. But look what's next down here. LD stands for light vehicle, right? 26% of it was while these people were in their light vehicle.
It means truck.
Sorry, yeah, like pickup truck. Heavy means like giant haul trucks and all that kind of stuff, right? And what we do is we also break this down by the individual task, right? And you see what floats up to the top is actual driving of a light vehicle, like a pickup truck or a light truck, resulted in about 25% of the exposure for that similarly exposed group. So where do you think we're going to focus our efforts? The light vehicle, right? Because that's where you can deploy engineering controls, better filtration, better door seals, window seals. How about administrative controls, cleaning, right? And requirements for how you operate, right? So this is the huge value with this, is that you can target your efforts. And so that's where you're making that jump from that one result to having some indicators to where to spend that effort. Very powerful when it comes to working with your management at your sites and getting their buy-in as well too. Okay, I'm going to shift over to our engineering controls and looking at cab pressurization. This is one of the key ones. Remember I told you we got like more than 400 pieces of heavy equipment. And so when we talk about cab pressurization, you look at the image at the top left and the bottom left, essentially what you're doing is you're taking the air from the outside environment and you're filtering it and you're pumping it into the cab, creating a pressurized environment so you don't get ingress of dust inside of it, so you create a safe environment. And dozers are a key example because just with how they work, they create a heck of a lot of dust, right? Tracks and blading and ripping and all that kind of stuff. So just want to show, this data here, this is from our first pilot of real-time personal monitoring in 2020. And we looked at dozer operators as a similarly exposed group. And so what you have here on the y-axis is your cumulative exposure metric, which we just went over, and the tasks along the x-axis. And it turns out that 75% of the exposure for our dozer operators were while they were operating their dozers in 2020. Right, 3/4%. Now, that's where they spend most of their shift, right? That's where they spend most of their shift. So, taking a look at that, we definitely recognize, obviously, we need to take some action on this. And when you look at, this is just from one of our sites, and this is the Land's exact 95% upper confidence limit, right? When you look at our sampling results from 2015 and 2020, our dozer operators were in the high exposure risk category for silica, right? So we implemented two things. We implemented increased filter changes. We're using the OEM filters, right? Not cap pressurization, and we were able to bring down that exposure profile based on 7 samples down to 96% for the Land's exact upper confidence limit. But then you look at what cap pressurization did, right? 64%. That's more than half of what it was originally. Right, so right away for us, key recommendations is you start installing these units on everything, right? Within, when I say everything, I say within reason. And then for those that aren't getting them installed right away, because you got to take a phased approach to these things to make it happen, is that you right away increase the filter change frequency. So huge success in bringing people's exposures down with this technology. Key thing is, though, is that there are some challenges to making this happen. But what I'm showing here is pretty consistent with what research shows for efficacy on these things. And what I wanted to show you is some lessons learned with haul trucks. Right now, we got many, many haul trucks and well over 600 haul truck operators. Right? And some of these equipment is old. When I say old, like they've been running for a while. So you imagine what happens to equipment over time. It's just like an old house. Things bend and change over time. And so we've got a picture of a haul truck cab here when they're doing smoke bomb testing to find sources of leaks. So these are really challenging to seal, right? There's more to consider than your windows and door seals, right? And just retrofitting with a pressurizer isn't enough. You can blow in as much clean air as you want, but if it's not holding pressure, then you can have dust coming in, right? And it's just not doing its job. The OEM designs, original manufacturer designs, they got different cab openings, right? The front of the cab, the subfloor, cable access, the dashboard, right? It's challenging to get that sealed. The other thing we got to talk about here is behaviors, right? Windows up all the time, right? That immediately defeats your system if somebody's driving around with their windows down. And then the other thing is that what you have to establish is performance, use, and maintenance requirements for this equipment. It's the framework that ensures once you put the equipment in that it gets maintained, it gets used properly, and that gets sustained over time. It's critical. You can't just go bolt something on because it'll just fall apart after a while. Just want to share some of our learnings and before and after pics. So what we have here, these are our 930E Komatsu haul trucks. What you can see at the in the before picture, up at the front there, that's the electrical compartment, which is underneath the dashboard. And what is that? That's an open panel with grating right there, right? So one of the key learnings here is, well, you got to retrofit this and take that off there, and we replace them with solid plates and sealed them, right? So you're cutting off that ingress there at that point. The other one here, this is looking at under the cab, right? So you look at the before picture, this is the subfloor, right? So there's cables and wiring, and that goes to the electrical compartment, which is underneath the dashboard. So what we've had to do is take closed cell foam and essentially block off all those openings. I mean, that's pretty big when you look at that. It's got to be like 3-4 inches, right? But then it's not good enough to just put foam because it's going to rattle out of there. There's still a crack. So we've had to go along and use this flex seal, this liquid elastomeric substance, to actually hold it in place and seal it right off. And the key thing is, like, this stuff takes 12 hours to cure. So that's an investment in time that we've put towards these things. Because if you know industry, when equipment goes in for maintenance, you're getting it back out there as soon as you can, right? And so we're investing this time just to make sure that we get these things sealed and setting correctly. Significant investment of time. And then, of course, we got our dashboards, right? Look at this. We got our infield fixes with good old duct tape there because these dashboards were cracked, etc. So what we did is then replace them with steel dashboards, right? So remember I told you there's the opening at the front, there's the subfloor, and that all went underneath the dashboard, right? So we're sealing off the dashboard. It's probably tough to see at the back of the room there, but that's one of the pressure gauges in the truck there, reading 159 pascals. So this has been our lessons learned and a success in pressurizing this older equipment. All right, here's the other thing is where do we go next, right? And so right now what you have are these crab pressurization systems, and they'll alarm when something's going wrong, but the operator has to act. That's all relying on the operator. And that's the behavioral element. So what we're doing, and we're right on the cusp of this, is being able to connect to these systems and get the operating parameters from them. So we got the pressure, we got the fan load, all these types of things. And with that, we're able to monitor and determine, hey, is there a slow decrease in performance? We got to get that truck in for maintenance, right? Or is there a total loss in pressure, et cetera? And then we can deploy our field maintenance there ASAP and triage it. And then the other thing you can do with that is manage your alarms. So for our mine operations, when there's an alarm going off, is that then they're able to act on it and get on the radio and say, hey, what's going on? You got your window open, or what's the deal, right? And with with the data from this and the smarts with somebody like Chris, who's the senior data scientist, we're actually able to apply methods that are again helping us predict this, help to tell the difference between like an alarm from a window down versus an alarm from like a system failure, et cetera. So that's where we're going with this. Okay, now we're going to move on back to real time, and we're going to take a look at our preliminary findings from real-time in-pit area dust monitoring. Okay, so what's the problem for us with in-pit areas? Well, one thing that we know is that our in-pit employees are at elevated risk of silica exposure, right? That's our issue. Work outdoors got its challenge with suppressing dust. And we got these massive environments. Look at how big these areas are. So we do use a lot of water and dust suppressants and all that kind of thing. But also at wintertime, all you end up doing is making snow and ice, which then creates its own safety hazards. Right? And wintertime can actually be one of those most dusty times. Right? You get a period with no precipitation for weeks and weeks and weeks. It starts to get dusty. And it's very variable. It's not always dusty out there. We got all this different weather coming through there. Right? So at times it's actually like there's no dust at all. Right? It's cloudy, it's foggy. It's our best nature suppressant. So with that variability, we got to keep in mind, like, how do we manage this? And here's the thing. So when it's visibly dusty out here, this is the requirement. You got to use respiratory protection when it's visibly dusty. Right? And that's so subjective and qualitative. Right? For the worker, for the supervisory staff, right? For our contractors. So what we need is reliable data. Right? We need reliable data to help us classify what the risk is at that time. And the other thing I want to touch on too is that conditions for when to use a respirator are just as important when not to. Right? If you make people wear respirators all the time when they don't need to, they're not going to use them. Right? That's the challenge you face there. So you have to be reasonable with your workforce and get their buy-in. Okay, so currently what we have, this is an example of our EVO's Elkview. That's one of our mining operations, and GHO's Green Hills. It's another mining operation. And what we have is an array of low-cost PM10 dust sensors around each of these mines for environmental purposes, right? And what it tells you is what those like estimated dust concentrations are outside of the pit, right? So seeing this as an opportunity, is that, hey, we can make use of this network here. We just ran a pilot, went through August through to December, and we deployed the exact same environmental monitors in pit, the exact same monitors. Right? And the whole point of this is, hey, can we do some hazard area heat mapping with these? And of course, doing it from summertime through the winter, so you got seasonality, right? And they're running 24/7. And the purposes for us, number one, we want to determine is, can the perimeter sensors predict what's happening in pit? And if we need the in-pit sensors, what's the ideal spacing and how many do we need? We also did co-located traditional monitoring to get an idea of how accurate are these PM10 low-cost sensors, right? How do they correlate? And then to see, hey, can we apply this hazard mapping and essentially be able to use it for like a geofence alert system for our workforce? And then, of course, you never just go do these things without coming back with recommendations and learnings to move forward. What's the next step? And so this gives you an image of what we've been able to accomplish. Right, so this is our Elkview operation. It's a triptych. It's the same map with each one. And we've been able to model the dust concentrations, applying a Gaussian model, and it's using dust concentration. This is based on a 1 hour average, and the latitude and the longitude. And what these little crosshatches indicate are the sensor locations for this configuration here. So you can see the type of resolution you can get with the modeling. And then also what we've been able to do is to put these risk categories in place for the maps as well too. So you can kind of see the transition to how you go from this to when you actually define the risk category. And just to touch a little bit more on that, what we've done, obviously these are PM10 sensors, so it's the total amount of PM10 dust that they're sensing, right? And once again, what we've done is scale it down for silica, because we know very well what that average silica concentration is in the air for the pits. So that's what we have here for our stoplight system, right? Green's okay, goes from 0 up to the action limit. Moderate risk going from the action limit up to the OEL, 0.025 milligram per meter cube, and red from there on. And so with this, you can see over time, this is just a 24-hour period of the variation that can happen in the mining environment, right? And the other thing to see is that often a lot of these sensors track together quite well. But at times you do have a bit of variability crossing that threshold as well. As I said, these are very preliminary results. Chris and the team are just working on finalizing them right now. Okay. One of the key interesting learnings that we got out of this is that dust concentrations in the pit can vary by day, or sorry, by time of day, right? So looking at part of our study period from mid-August to mid-November, the x-axis here is time of day, right? So that's midnight going through till 6 o'clock and back through to midnight. And then what you have on your y-axis, 0 is the average dust concentration. And if you go up in the positive range or negative, it's how much it deviates. So this means dustier, that means less dusty. So what you see here at nighttime is actually you have elevated dust concentrations. And then during the day, it actually drops down, right? Afternoon comes along, evening sets in, and it goes up to be more dusty. And this is critically important if you want to start strategically deploying your controls, right? Think about dust suppression and when you need to focus a lot of your efforts. The other thing is also from a hygienist perspective is doing, ideally we're doing randomized sampling across seasons and times. You really want to make sure you're getting your samples out at nighttime to get an accurate risk profile for your workforce. I have a hypothesis on what's happening here, and Chris has helped dig into some of the data there, and it turns out wind is good, right? And usually what you see is as wind goes up, the dust concentrations go down. And what you have happening in the mountains is typically you have sun coming down to heat the side of the mountains, heats it up, the hot air goes up, and the cool air comes in to replace it, right? So think about it, it's like nature's general ventilation, right? But at nighttime, the sun disappears, and you don't have that convective process going on, and the dust essentially sits and builds at that point, unless you have some big weather system coming through. Okay, getting at answering the question, do the perimeter sensors predict what's going on in pit, right? So the model that Chris has built essentially predicts what the values are for the risk category in the area, right? And then what's done to test it is then you then compare the predicted value to exactly where that sensor is right now, right? So when we take all the data points from all the sensors, the in-pit ones and the environmental ones, what you see is the risk classification error, how frequently. It's essentially an indicator of accuracy. What we see for our Elkview and Green Hills operations is that we're having a risk classification error about 3.5% of the time, which is pretty good when you look at it. You flip that around, that's like 96% of the time you're predicting accurately what that risk classification is. Now, getting at, hey, well, how does the perimeter do for in-pit? When we actually remove these yellow in-pit, IPAM is in-pit area monitor. When you remove those from getting input into the model, and you're just modeling with the perimeter sensors, and then you compare to the actual real deal values there, what you see is that there's an increase in the error rate, right? The accuracy goes down, but it's marginal, right? So it's actually doing a pretty decent job, and this tells you the difference there is that it's about somewhere between 0.5% or 1% of error attributable to having those sensors there or not. So huge value in having those sensors in pit. Marginal improvement, but I got to tell you, probably the greatest improvement there is for your workforce, right? And having 1 or 2 reference monitors there will give that workforce trust in the system that you've deployed. Because you've seen those pictures, our pits are really big, right? And you want to make sure they bought into it as well, too. All right, answering another question here. This is just a little bit more qualitative, but Chris is on the verge of the data here to indicate when you need in-pit monitors, how many and what's the optimal spacing. And so just want to show you the example of the picture on the top left here. The tight array at the bottom right corner of the map is actually around a shovel shutdown. And that's what these 3 pictures along the top show. The placement of the sensors, and gives you an idea of distance, right? So that shovel will be down for a week or 2 weeks. And we set up the 4 sensors around it, right? And I know it's tough to see here, but this was our in-pit area monitors, 5, 6, 7, 8, the EVO ones. And really, you know, if you pick the colors out, and for those who are looking from home or wherever, is that they actually stick together really tightly. The variance is quite small between them. So the value in that is that you don't need to deploy 4 sensors in a small area, right? You can get away with deploying 1 sensor. And what that does then is it frees up your staff, your team to go do other things. And the money involved with this, you can instead, if you have a bunch of sensors, go deploy them elsewhere. You're going to get a better picture of what's going on in that in-pit environment than focusing them all in one area. You could just deploy 1 in that area there. Okay, lastly, correlation between traditional monitoring with a pump and a cyclone and a filter and sending it to the lab with the PM10 sensors. So traditional pump cyclone is shown in blue, and the orange is the PM10 sensors. And there's an image here when we had our tripod set up next to each other and at our pits. And this is based on half the study period. We're just working on the rest of it. The long and short, there is no correlation based on the sensors we're using, right? Which I was expecting the PM10 sensors to show more. You know, when you do look at the curves of the fractions, you would expect more to be there in a perfect system. But it wasn't the case. And talking with the manufacturer of the sensor, they calibrate their sensor to PM 2.5. And then they mathematically scale it up for PM10, right? And then another thing that was shared is that the sweet spot for that sensor was at 1 micron for it to respond to. So what that says is, man, you got to make sure you got the right sensor for your environment, right? You really do. But once again, you know, this is a modeling exercise and using an apples to apples comparison for those in-pit monitors to the perimeter ones, right? Had we gone and taken way better sensors and deployed them, you'd actually have a kind of a bias or confounding factor when you're comparing to these other PM10s on the perimeter. All right, at the end of the day, recommendations, and we already got recommendations at this point here. You know, optical particle counting sensor, some technology with that. So if you can do PM 2.5, PM 4.5, or whatever it is, PM 4.3 for residual fraction and PM 10, you got a major win-win there because you can get a sensor that's going to work for environmental groups and for occupational health. Light scattering sensors on their own just aren't going to cut it. You need to deal with humidity, right? Whether you're cooking it out of the air or correcting for it. We had our highest exposure results ever on this network when it was like foggy, humid, wet rain, and there's like no dust. You got to get the highest off-grid sampling frequency that you can, because there's certain periods when you can sample, and then you got to charge for solar battery and then transmit data. You want GPS. That's Kendall. She's our technician who worked on the project, taking a GPS location because the monitors can do it themselves, right? And then you also want an accelerometer because these things get knocked over. You want to know that it's sitting on the ground or is it still up getting the right air, not just ground air. You want to validate periodically, right? Make sure that you got accuracy as high as possible. And then the biggest piece of this is operationalization. What do you do with this data, right? So you got to develop an averaging period that's protective of worker health and also practicable for the workforce to respond to, right? You got to have a strategy for risk category warning communication. How do you actually get that out to the people, right? You got to engage your key stakeholders, right? All your operations, your workforce, your union, what's going to work to make this happen, right? You got to follow management at change. right? How do you actually deploy this thing and do it in a way that it gets embedded and sustained over time? And then you got to have change management, which is that effective communication of that management change. So everybody knows their responsibilities and what they have to do, how they need to respond, and how we're going to make this happen over time. And that's where we are now, moving into that. All right, so bring it back to our vision. We're really confident with using real-time technology and deploying engineered controls. We're going to get there, and we'll have all our segs at lower moderate risk categories for silica. And that's exactly the path forward, and we're confident in it. That will open it up for questions and discussion.